Good morning, everyone. Thank you for coming. This morning we're going to hear from Matthew Holden, who's a mathematician trying to reveal fundamental principles of effective conservation and environmental management. And today he's going to talk to about value of information analysis and how we can work out whether it is actually financially viable or worth it to go do field studies.
Thank you. It's wonderful to be here. I'd like to start by acknowledging the Turrbal and the Yagara people, the traditional owners of the land on which we meet, and just noting that this land has never been ceded. I'll start by thanking people, just in case I forget at the end. I always like to start thanking people. This work has been done with Dr. Yadin Chavez and Deborah and Kate Helmstead at QT and Frankie Cho, who's in the room, and Allison Binley. I'm also going to steal some slides and ideas from Hugh, this very attractive photo. And then does anyone want to venture to guess who this person is? Yeah. Yeah, that's Eve McDonald Madden, actually. I think I found the youngest photo of Eve on the internet. But it is a photo of her actually doing field work before she came over to the dark side of mathematics.
Wait, that's not right for the Aqua Valley Institute. We're trying to say frogs or something.
Exactly. And so she's done lots of hands-on work on saving frogs, and we're going to talk about frogs in this talk. So I'm going to talk about how much effort should we spend gathering information. And before I go about talking about this, I'd just like to ask, why should we collect information? The first thing is to inform decisions, but does anyone have any other reason why we might gather information? Why might we just science? Anyone want to volunteer something? I'm just going to make this very interactive so I can talk less. Yeah. Work with communities, that's great. So involving the community.
Just want to know stuff.
Just want to learn, just the information has sort of intrinsic value. So yay, science. Anyone else? So there's lots of different things. So public, just want to learn about the system. Auditing, holding people accountable. We do that a lot, but we maybe don't do a good enough job of it. And surveillance, trying to find things, tests and outbreaks and whatnot. Here's a reason. How about it's just fun to do it sometimes? Like, I actually enjoy doing abstract mathematics that seems to have no point. So why shouldn't you be able to go out into the field just because you enjoy it, even if it doesn't matter? So I'd like to pose to everyone this case study. So this is a really classic case study in the literature. It's trying to look at endangered frog and see if this translocation strategy is going to work. But in the site that you're going to translocate it, there's some chance that there's a fungus there that's deadly. And you don't know if there's a fungus there. So you can do a field study and check to see if the fungus is there and resolve that uncertainty perfectly and to find out whether it's there. Assume that it costs $100,000 US, let's say a postdoc salary, to do that study. And let's say the translocation cost is free. You can get a donor to cover that, especially if the scientists tell the donor it's the best action. So here is the values. We'll just assume that the baseline population of frogs, there's 100 of them, just easy math, 100 frogs. If we translocate, we take some frogs and we move it to the other site, but the disease is present, a bunch of those frogs die, but we only have 55 frogs. However, if the disease is not present and we translocate, then those frogs do pretty well, and we get 135 frogs across the two sites. So this is an example, and let's just say prior to doing the study, we think there might be the disease present with a 30% chance. So I'd like you to talk to your neighbor right now and ask, would you spend $100,000 to learn whether the disease was present at that site? So talk to your neighbors now. I want it to get really loud.
Yeah, well.
All right, settle down. Okay, I'd like to take a survey. How many people say they would do the study? Raise your hand if you would do the study. Yeah, good number. How many people would not do the study? Okay, about 50-50. Okay, so that's good. That's good that we have some controversy. Okay, so I'll go through a calculation. I won't describe the theory behind it just yet. I'll wait and do the sort of fancy math later, but we'll just walk through it. So first we could look at the expected value under uncertainty. And that says under uncertainty, I don't do the study. I didn't resolve the uncertainty. Well, what would you do? You would check the two actions. So I don't do the study, but I have two conservation decisions. Do nothing or translocate. So I can just walk through the math and say, I have these uncertain probabilities. I can weight the possible outcomes, and I get 111 frogs on average. If I do the translocation, if I do nothing, I only get 100 frogs. So in expectation, I should do it. And then I could go through the same calculation, but this time I get to do my study first. So if I do the study, I resolve the uncertainty and I say, well, if the disease is present, I'm not going to intentionally murder the frogs. So I get 100 by just doing nothing. So I choose to do nothing in that case. And if I find the disease is not present during the study, then I do the translocation, and then I just average those two outcomes, because before doing the study, I actually don't know whether the disease is present or not. So I have to sort of like make up based on my probabilities of what the expected value is, and I get on average that I would get 124 and a half frogs. So the expected value, and we'll call perfect information. I'm going to be using perfect information a lot through this talk, but just note that all the other types of value of information calculations are always lower. So this is the best you could do. This is very optimistic. So in this case, I got 13 and a half frogs from doing the study. So that's the expected value of that information is 13 and a half frogs. Well, so you're all right, because whether 13 and a half frogs is worth the $100,000 in monitoring, right? That's a little bit less than $10,000 a frog. Maybe that's worth it to some, not worth it to others. That's really a value judgment. All right, now I'd like to change the example, right? So now imagine if the fungus is present, I just wipe out the species, because maybe I removed some, and then by removing some, the population was too small on the other side, they just both died. So maybe just imagine that, or maybe there's some transfer between and the disease just spread them both. So imagine this really worst case scenario of now the disease is present, I just kill everything. And it's really uncertain, there's only a 0.01% chance, but I get a 0. How many people, so I want to see a show of hands, in this case, compared to the last case, where there's this really uncertain, there's this really extreme outcome, would be more likely to want to do the study? Show of hands, how many people would be more likely to want to do the study in this case? So a decent number, right? Because it's a really extreme outcome. Well, let's walk through the math. We can go through the same calculation. All right, 133.65 frogs versus 100, so I choose the 133.65. I keep on doing what I've been doing. And 134.65. So on average, 1 frog. So the value of information in this study was, if I did it in this case, is only 1 frog. That's less. That's less than the other case, even though it was a 0, we're wiping the population out. So that seems really weird. Yeah, why is that so low? Well, we'll resolve that later. How about, let's change it again. Now it's 0.99 and it's a 0. Now how many people think it's more likely to want to do it this time? Okay. Yeah, so we can walk through the calculation again. Blah, 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 math. 0.35 frogs. So only a third of a frog this time. That's even lower. This is looking really bleak. So how much effort should we spend gathering information? Well, it turns out, according to maths, very little. And you know, Hugh was given sort of a version of value of information talk, why should we monitor? And one of the classic things he's mentioned is we should stop learning about how climate change will affect puffins if you're not going to change your action based on that information, right? So the expected value of information in that case would be 0. And there's koala populations. A bunch of people in this room have shown that for learning, the value of learning things about koalas is about, you don't want to spend more than 1% of your management budget. It's kind of wild given that most agencies, government agencies, spend about half their budget on monitoring and information collection. So what is this? So this is what the paradox. This is what I call the value of information paradox, is that the math always is saying the value of learning is so freaking low. And yet intuitively, we think it should be high. And whenever we try to cook up case studies that, this time it's gonna be high, and then you get 0.35 frogs. So what is going on there? So to understand this, I wanted to ask, well, is the value of information ever high? That's a question. And what is the maximum value it can be? And so this is the fanciest equation I will have in this talk. But you don't have to worry too much about the equation. Just note that A is the action, S is sort of an uncertain state of the system. And I'm going to use this term U to just say my benefit, my utility. So the utility of taking action A, given the system, is in state S. And so this first term, this is just the table. So just sort of, you could zone out a little bit right now if you really dislike symbols, but this is really just the table. It's just saying the value of information is the utility of taking the best action after learning minus the utility of taking the best action if we don't learn. I saw a paper by Mike Rudd, unfortunately, right about a week before I was going to submit my paper, so a little bit rough there, but he had this beautiful graph. So I really like this graph because it explains why the value of information is so low logically. I did my proof using lots of just calculations and letters, and that maybe yields less intuition. So here on this x-axis here, I have the probability. So imagine I just have 2 states. So this is the easiest value of information. 2 actions, 2 states. It's just like the frog example. So here on the x-axis, I have the probability that I am in the system is in state 1. So over here, the probability is 0, so it's in state 2. So that's why there's 2s for the utilities over here, because I'm in state 2 over here with certainty. And over here, I'm in state 1 with certainty. And let's just assume in state 2, action 2 is better. So that's why U22 is higher than U12, and vice versa. If I'm in state one, action one is better. By the way, if one action is always better, regardless of what state you're in, can anyone tell me what the value of information is in that case? Zero, right? Zero. So the only time there's a non-zero value of information is if you have this sort of swap. Okay, so let's first look at the value of resolving uncertainty. So this is just the benefit if I resolve the uncertainty. So the first term in that equation, well, it's really just the average based on the probability, right? It's that expectation. So it's the average of these 2 points based on whatever the probability is. So I'm just along this line. So that's the first term in the equation, is just the connection of this top line. All right. Now, remember we have this swap. So I'm just going to draw 2 lines that intersect, right? And just note that they intersect at some critical probability, P star. We'll define that as P star as that intersection. Well, this is the second term in the equation, right? Because it says if I resolve the uncertainty, I actually take the best value, right? So it's the max of those 2 lines. So over here, I pick this value, but once I'm across that probability, I think I'm in the other state, I'm going to pick the other action. So there's the swapping, right? So the value of information is just the distance between these 2 curves or lines, right? And so the maximum possible value for value of information is at this critical P star. So this is the maximum possible value. If I move to the left, if I'm sort of the probability is lower, then the value of information is very low. If I move this way, the value of information is very low. So it's always at this critical value, and this critical value is always at the intersection of those 2 curves. And you could quantify that with some math. I won't go through the details of that, but note that it's based on what I like to call the utility gaps, which means it's based on the differences between these 2 values. So we define these 2 utility gaps, and it turns out the value of information can never, ever, it doesn't matter what your system is, it doesn't matter if you're studying frogs, you're studying chimpanzees, it doesn't matter. It's just based on the mathematical construction. The value of information can never be half the maximum utility gap. Which, what does that mean? Well, if I have let's say all my benefits are positive, I can never learn and then somehow get triple my frogs. That's not possible. You can never do better than doubling your frogs in expectation by learning. Doesn't matter anything special about your system, you can't do it. So that's sort of the theory. It says what the maximum is, but most things won't be at the maximum. So we just generated, like hundreds of millions of random 2-action, 2-state systems. We just filled in those matrices. And then we asked, well, what's the value of information in sort of random systems? Well, the answer is half the time, it's 0. So half the time, the value of learning is nothing. You shouldn't even consider it. And then most of the time, it's very low. So this scale is proportion of your benefit function. So most of the time, you're going to be less than 10% of your benefit function in learning. Now, sometimes if we're dealing on the orders of billions of dollars or saving a species from extinction, maybe 10% could be good. But in general, the numbers you're going to think of them as quite low if they're always less than 10% of your benefit function. And so on average, the value of information is 0 in this 2-action, 2-state system. So on average, you can expect to gain nothing from learning. If you increase the number of states and we still say we have a random system, then the expected value of information does on average start increasing if you increase the number of states, and the uncertainty in that, or the variation of value of information sort of narrows a bit. These are all simulations, so we haven't proved anything there. So we're still sort of looking at this. This is all sort of preliminary results. So why do these results feel so wrong? Well, one reason you might have already been thinking of is that you're constantly taking these expectations or averages, but averages don't capture risks. So maybe we should develop risk versions that factor in risks in our value of information calculations. And so Kate Helmstead and Matt Adams and Deborah at QT, she is looking at this. And I think that paper is currently in review. So what are some other reasons? Well, one possibility is that, well, it's only the value of information to make the decision. We're not capturing everything else in the big list. That's a possible valid criticism. Here's me in the field, enjoying myself, I think, doing some quadrat sampling for John Dwyer. He managed to convince me to do this. No, I was not invited back.
You're also in a cemetery.
Yeah. All right, so but here's one thing that I'd like to think a little bit about. One of the things when you calculate the value of information, you are assuming that the person who didn't get the information, who chose not to get the information, is going to factor all their uncertainties perfectly and make the best decision, sort of factoring in all their uncertainty. You think these people do that? I don't think so, right? So often I would say that the value of information might be value to sort of hold people accountable and prove something that forces them to change a decision. And so value of information analysis won't get that into their calculation. And then there's also the possibility that maybe new information can lead to new actions. In which case that you've only considered some actions in your table. If you have new actions that aren't in your table, that could potentially be a game changer, and maybe it could lead to more money. So that would be a potential, although I still really haven't found examples of this. So if you know of examples of that, you should come talk to me because I'm really interested in that. And then I said in the abstract, I promised that I might mention something about this topic of whether we need more protected areas. And I'll just say yes. And that's work that just came out by Phil Erm at Cambridge. And if you're at Morning Tea, you've already seen this, but it really assumes that your protected areas are enforced. And with that, I'll take questions and leave photos of species that were in the house I got kicked out of up here. That's it.
A question.
Yeah.
Actually, so in the first frog exam, we had beliefs, it's like 0.3 and 0.7.
Yeah.
But what about when you don't know what belief to even have? Like,
Yeah.
do you model it as a probability distribution, and how does that affect everything else?
Yeah, that's something that I've always been grasping at, and I currently have written sort of a grant proposal on that. That was rejected last time, so we'll see how that goes. But yes, I think the value of information assumes that the decision maker can even put probabilities down on paper. You try and get a scientist to put anything down on paper, it's a pain in the butt. So yeah, it's a pretty big assumption, and it sort of assumes that there's no bias in that probability. Like maybe they'll be biased towards a incorrect version. So, but what sort of the Bayesian decision person would say is that it's reasonable to assume that the person's sort of probability or best guess sort of is the truth, as as the prior. So it's the expected value of information to the decision maker given their belief. So that's what probably the Bayesian decision theorist would say. I'm not so comfortable with that argument, but at least that's what the people who reviewed my grant said. Yeah.
Kind of on a similar like track of that last question, I guess like for those priors to be built into that hypothetical situation, like doesn't that itself require like research, inquiry, and like monitoring, like to even know that you're gonna get 100 frogs out of it or not, or I mean, even just the basis of it would require a lot of justified field work, no?
Yeah, so like the question being, right, like to even, if you can specify probabilities, you know something about the system, right? Like, so you've gotten some information at some point, so you had to do some field work, or you had to talk to experts, you had to get some intuition, you had to do something to get those probabilities. So yeah, you're not starting with sort of zero information in that case. You could always, so what probably the Bayesian decision theorist, I'll put on my Bayesian decision theorist hat, they would say, well, one thing you could do is you could just say it's 0.5. And, or just say it's P, if you, now that we have this theory that we've developed, you can now just even say it's P star, right? And you're definitely not gonna get anything better than P star. So, you could be conservative and just say it's P star and go through the calculation with P star. And you'll get something out based on just those utilities.
I think just developing that one a bit more, doesn't each piece of information kind of pay forward to future projects by taking what you just said to the next step? So in some ways it has like an infinite forward payoff, finding out a little bit more about frogs or about conservation in general.
Yeah, possibly. The thing about that though, is you can formulate the decision problem in this value of information framework by imagining you're the person at all the way at the end. So you're imagining what's the benefit of this information, that one, and you could calculate it that way. In some sense, the value of information, this is, if you formulate the problem in the most conservative way possible, you will get an upper bound that is even higher than the value of doing a sequential optimization where you're doing sort of like active or passive adaptive management or dynamic programming or any of those fancier things that we like to do on the 5th floor of this building. Those fancy things, this is actually sort of a really, I mean, the math might have been scary, but like it's one line in R to like basically do this calculation. I mean, the setup is the big cost, right? Just importing all the data and like writing it out. But once you have all your data and the calculation is pretty simple. In fact, often people ask like Mike Runge, do you have an R package to do value of information for me? And he said like, no, do it yourself. It's one freaking line. No, that's his answer. I think to myself, oh man, I should write an R package. I get so many citations for one line of code. But that's maybe a little less ethical than mine. Anyway, yeah. So a lot of you could do this calculation and then use it if the value is high. You then would want to do the fancier stuff like the sequential optimization stuff. But if the value is really low, you might not even do information at all. Assuming you were comfortable with all those assumptions that I'm totally not comfortable with. I think Eve had her hand up for a while.
So many things to say about tomorrow.
Yeah.
Rich, were you also saying that there's like, it does pay forward in terms of decision making, but also there might be other benefits to it? Like learning more about frogs in general, which is another reason to monitor.
And future decisions that we don't know about. It's partly what you were saying, I think. You sort of talked about we're learning other kinds of information as well.
Because sometimes the other reasons to monitor stuff have their own like versions you can do that aren't so decision focused about attitudes. But I can imagine if you were trying to prioritize monitoring and doing this as part of it, you would also have to say, okay, like, how do I divide that cost? So if I've got 100K, how much of that money is going towards the increase in frogs and how much of it is prioritizing future information for just general frog stuff? And then you have to weight that as well. How much do I care about this? So that would be a trade-off. So you could do it, just get more complicated. And
Yeah, go ahead.
if I
Just keep,
Is that all right?
keep going.
I was gonna say to the belief stuff, like how you come up with that, at that number. You're pretty, like, it's hard to think about how you would do it, but there's pretty rigorous solicitation processes for getting people to think about these types of things. So it is based on, like a Bayesian, all the accumulated information that people hold and all their biases. Trying to avoid those and elicit those values and getting different values from different experts and doing that in the Mark Bergman-esque, best way possible, getting yourself to the best estimate of those gives you the best chance. So there's good ways of doing it, there's no perfect way. That's
Yeah,
right.
I think,
But Matt, I was gonna say to you, like, there's some inherent trade-offs in here, but one of the big things I think is, particularly when, like, I teach this, I'm talking to
Yeah.
frogs and their two beliefs.
yeah,
Right, there's always way more action.
Yeah.
There may be 10 actions. And you do it on that one objective of frogs. But that same monitoring action could be, there's information related to maybe 10 other objectives that we
Yeah,
care about. And I think, have you guys started to think about how you might deal with that aspect?
we haven't thought about that beyond just waiting. Right,
Yeah.
but ideally, right, if you go to a decision maker. You'd like to give them a trade-off curve and sort of elicit what their thing is. But that would start getting very complicated very quickly if you did monitoring for trade-off curves, although that's quite interesting.
And from that paper that you showed that Sean did,
Yeah.
I think one of the most interesting probably parts to me about value of information is the value of, again, add another term, value of partial information, which is, of course, it's always less than that conservative estimate, but divides it out across your uncertainty. So an example might be if you had a system model.
Yeah.
With multiple components, and you didn't know which part it was, like, was it uncertainty about birth rate, death rate, or how many koalas die from roadkill versus habitat or whatever.
Yeah.
Being able to divide it out and say, like, if we hone in on this particular thing and learn more about that, we can increase our utility by heaps, whereas if we're generally learning, it's not worth learning about it. Sometimes it's quite a useful tool.
Yeah.
That's we want to manage anyway.
So I
Manage
think,
anyway, sorry.
yeah, his point about the value of partial information, the idea there is you can go through these calculations and look at the value of collecting different types of information. And in some sense, that's the most useful time to use this tool, would be if you're given a management or a monitoring budget. Because if you're given a monitoring budget and you already know, like, this is the monitoring budget, then you're gonna spend it, otherwise the government will just take it away and you won't be able to do anything with it. So, in that case, you could use this tool to calculate what's called the value of partial information, where you look at what type of survey should I do? And then that gives you a nice scale to weigh the different types of surveys, because they're all sort of in terms of the same outcomes. You could say, is surveys type number 1 more beneficial than survey type number 2? And then you might say, oh, it doubles the value of the information, then you would choose survey type number 1, right? And that's probably one of the more useful ways to do value of information. And you could also do that for learning parameters and models, or learning between models, and all sorts of stuff. Yeah, so that's a really useful avenue of when you might use this tool.
And that's the talk that Matt will be giving at the end of the year.
Yeah. Yeah, maybe.
Question online from Yanni Chadheads. Matt, can you clarify that the calculation of VOI here is about maximising management outcomes, not maximising knowledge?
Yes,
And if we want to maximise knowledge, then it's experimental design, then it can be optimal to monitor.
Yeah, right, so that's key, right? We're only talking, so at the very start of the talk, I said, we're only talking about management decisions in this talk. And that we swept all the other reasons why you would monitor under the rug. So if you wanna maximize your learning, that's a whole different problem. That assumes you're sort of already gonna do some learning and you want to learn. That's that's optimal design theory, which is a different field, which I did not talk anything about. I only talked about management outcomes for decisions. Yeah, thanks you for emphasizing. That's really important. Yeah.
What I would love to know is if time is of the essence, it's possible that while you are trying to optimize your studies, the population will disappear.
Yeah.
You haven't factored in time at all in your equations.
So you can, in fact, I would say that usually would mean that you'd wanna learn less. So, right, you wanna just act, just do the thing that's best, do it now, when the population is declining, the frogs are dying, just act, yeah. So a lot of the time when you wait, you can monitor a population to extinction. You could watch a population decline. And is that very useful? I don't know, maybe it might be useful for learning, it might be useful to try and convince someone to act, but ideally, if you had the money, you would just actually not spend it on monitoring at all, and you would just take the best action now before it's too late. Yeah, so absolutely.
A comment and a request. At one point, I was a manager of a $10 million a year research fund for wet tropics, and by far the most value we got for research was on the most esoteric projects that we ever funded, which was actually to develop a method to find out what insects there are in trees. The question is whether the methods that you're developing could be applied to, as an ecologist, to the systems we'd like to understand. From the frog's point of view, are you better hopping out of the pond and exploring other places? And from the population of frogs in the pond, do you benefit from having some explorers who go off? It's the same problem that Polynesians faced, colonization. So from the standpoint of colonization, refugia, survival of remnant populations, it seems to me that your approach might have some application when considering optimal strategies if you are an explorer or a stay-at-home.
I think this does get back to Yadine's point that these methods are for management outcomes, but in the frog case, you might have a management outcome like surviving. Like if you're imagining frogs are putting on their Bayesian decision theorist hats, and so you have a bunch of Bayesian frogs hopping around doing math calculations. Maybe they could do some action, explore the space, and do something that saves them. Maybe and maybe there would be tools to identify things like that, but if you're just talking about sort of like maximizing learning, you're saying that when you were managing that big group, some of the most successful projects were really esoteric, where there was big benefits just from a learning perspective. That would be the optimal design theory that Yadine was talking about, that you probably would want to swap to rather than this management outcome space for value.
My question was, related to that management outcome. So the example you gave was, like you have an existing population and you're doing management. But does your value of information equations also apply to restoration, where you are potentially doubling, because you said, it's not possible to double the number of frogs, but could you apply it to restoration management, where you are doubling the outcome or the benefit or the utility? Doubling population numbers or doubling habitat.
So
if you don't have an upper limit, is it difficult to apply that?
it's important to make the distinction that you can't double the frogs over the best action if you didn't learn. But that's not the same thing as saying you can't double your frogs, or you can't triple your frogs, or you can't quadruple your frogs. What it's saying is you could have not learned and maybe tripled your frogs. That means by learning, you won't sextuple your frogs, right? So it's all relative to the learning. So in like the restoration case, you might quintuple the amount of habitat, right? You definitely can go past double, but it's saying that by doing some sort of field studies or getting some information, you won't double it over the best restoration action if you didn't learn the thing, right? And that's something that a lot of people, when I present this, sort of think that as well, because we're so entrained as ecologists to think about the population and doubling the population, tripling the population. But yeah, this is all relative to sort of some counterfactual fantasy land where you didn't learn or did learn, and you're just sort of, I mean, that's one of the big problems with this method, is it's assuming that in the absence of information that you're going to take the best action, even if you didn't do the study. So these people are going to, let's say, triple the habitat for mangrove, which seems quite unlikely.
This question is a bit naive, but to me it seems that math or formalized methods are very good when you know where you are, that they can take you to a different location, like you know your assumptions, you can build a good model and it brings you very precise to new information. But the problem that you're presenting, it's exceptionally complex, and I guess many problems that technology face are so complex that I wonder, are formalized models or formalized approaches such a good tool, given that we can't really make the assumptions match the complexity that we have, and so the direction that the models take us, they are very giving the assumptions, but the overlap between assumptions and the problems that are out there is so large that the model either somewhere in space, but you don't really know if that's useful.
Yeah, that's an interesting question. That's a question I asked during my PhD a long time ago. I had sort of an existential crisis where I was like, oh, I'm in this math department and I'm struggling doing all this complicated mathematics. Is there really any chance that any of these methods really improve the population in the real world, where there's all these complexities, your models and your methods are gonna not really apply, all your assumptions are gonna be completely violated? Do these totally wrong, totally terrible methods have any chance at offering it improved decisions? And so what I did was I developed a little computer game, and I tried to convince teachers of undergraduate courses that they needed for me to let me give a guest lecture where I would just get students to play the game. And apparently a lot of people at universities do not want to give their lectures. So I got into a few classes, a few big ones, and ran this experiment where people used intuition and sort of their knowledge from their coursework or the real world experiences to manage this hypothetical computer game. And then I had I had some pre-designed methods of these tools, these mathematical tools that were going to manage this hypothetical computer game population, using totally wrong, incorrect models fit to the data that was coming out of the computer game. But I was saving the outcomes of like the random number generators so that both the computer and the human that was managing the population on their laptop saw the same reality as to what they would have done if they changed their actions. So they were both managing the same exact sort of population. And in that case, some of the humans did beat the mathematical methods, the incorrect mathematical methods, but on average, the mathematical methods still ended up winning out about 70% of the time. So I would say that probably the benefit of going through the mathematics is it forces you to state your assumptions and be sort of really transparent about it. And it will reveal things that is sort of stuff you're maybe just doing sort of informally in your head anyway. You still have the same biases, the same sort of human issues that you have, whether you used a model or not. The model is just an artifact of the human anyway. So you might as well do the good mathematical thing with all your human biases, but it forces you to state them all. So that's what I would say, but yeah, it's still sort of up in the air, I guess, to some degree.
Yeah, there's a massive pioneering consulting company in Canada that runs decision analysis for business instructions in like what I call it. Well, heaps of different massive problems, like huge, very complex problems with Indigenous communities and multiple values and maybe the whole watershed or something, or whatever. And what they've shown over time is the process of working through a problem with stakeholders and essentially setting up a mathematical problem. In a way that I call it that, control variables, whatever, but like objectives and utilities and different things. You're getting to a point where you have all that down and have just the values of what could happen under different scenarios. Usually gets the decision makers to a point where they can make a choice without even doing the analysis that compares that. Like it's just the information and the assumption. A lot of the time they'll run these huge problems and get to this point, and then the decision makers, the ministers, the manager of the park, or whoever, will way more comfortable about the choice they're going to make because they've captured that all in there. Essentially defining a mathematical problem without doing it and not doing the optimization at the end of the multi-criteria decision analysis or the value of information analysis or any of that stuff. Just getting to that point. So it's worth it, whether or not you go to the negative part at the end and do that stuff. Really depends on what you're trying to do.
When if you have a complex problem, you decide if this is something for math or no, or do you just try?
Well, I think, and I think Eve hit on this. One step is to just sort of step through what you think your assumptions are and do some like mind maps and things like that. Often those sort of things that you write down can be translated in equations later on. But it's actually the process of doing the stuff before the modeling. And in some senses, the most useful part of doing the modeling is going through that sort of more rigorous thought process, even if you're not going to do the math. But then also once you've done the thought process, you've done the mind maps, stated your assumptions. If you feel like, oh, I have no idea how to turn this into math, you know, you can talk to lots of people here. There's lots of people here who do mathematical ecology, mathematical conservation, mathematical environmental management, and you can go to them. Once you have something that's more defined and structural with your assumptions, it's a lot easier to talk to a mathematician. You walk up to a mathematician and you're sort of all over the place, like they'll just like, I mean, I'm more used to it, but I think a lot of us would be like, oh God, what is this? So like the more you've thought through the assumptions, even if you didn't do the math, the more you sort of think about the pre-steps to being a mathematician, the easier it is. But you kind of have to work through that before you decide whether math will be helpful or not.
There's been quite a discussion online. They're talking amongst themselves and sharing papers about optimal stopping.
Okay, yeah.
And there's been a couple of comments such as Hugh saying usually should spend 0 to 3 years learning fairly more.
Yeah.
Mike Runge has said his point is great, and I think that's why we perceive a paradox. BOI compares a well-framed decision in the face of uncertainty to one in which uncertainty is resolved. What we really want to know is what's the value of framing the decision in the first place. It's probably quite big.
Yeah, exactly. I think Mike's really right. It is about that framing. And there's lots of problems in the sort of optimal stopping time literature. I won't get into that, but
There's also that kind of optimal reframing. I think Mike, talked a lot about, and you think as well, this is like double loop learning, it's kind of like, should I learn and manage and learn and manage? Whereas if you're in a triple loop, you're saying, is my system still the same? Have I captured everything? Are my assumptions correct? And when should I reframe my problem? And that doesn't mean you're stopping necessarily. It means you're reframing, going again. So triple loop learning is then straight outside and just not very good.